Welcome back to Series 3 in the Atari ST Nostalgia GFA Basic Tour. In the previous video we created some nice animations by buffering and swapping screens. But in the end it all got a little bit slow, and in the rest of this series I want to explore other ways of doing the same things, but faster, and also maybe do some fancy stuff addition to that. And this will require us to work much more direct into the system memory. So before we continue this series I will go a bit more into the theory on how to prepare for these direct manipulations. And to show it I actually create a little bit of show and tell code. Because remember, in the first video we talked about how all graphics commands are basically just commands that create a bunch of bytes and put those bytes in memory. And it's also true the other way around. So graphics commands result in writing bytes, but also writing bytes into memory can actually result in graphics being displayed on screen. And I created this code to show you just that. So I'm going to do the same array to create this pre-draw buffer and buffer screen address like I did in part 29. But this time, instead of telling my graphics commands to write to that buffer screen, what I'm going to do is actually I'm going to tell my video shifter, so the graphics commands will remain in the default configuration, but I'm going to tell my shifter to read somewhere else, so to read from this buffer screen. Which means at that point, if I execute the graphics command, it will still generate the bytes and it will still put those bytes into memory, but the shifter will no longer be looking at that location. So on screen we see nothing happening. Thus sort of proving there's no way I can use a graphics command to put any data on screen. What I'm going to do next is actually I'm going to manipulate the data inside the array that's actually holding the memory space that the shifter is reading from at that point, so the pre-draw buffer array. And I'm going to just write a random bytes into every element in the for next loop, and we should see something happening on screen. And then I'm going to use the array fill command 3 times, and I'm going to write values that corresponds to a very specific binary pattern. For instance, the number 240 will result in 4 ones and 4 zeros, which in monochrome relates 1-to-1 to 4 black pixels and 4 white pixels. So we should see these patterns appearing on screen, and it gives us an opportunity also to see how much faster the array fill command is actually compared to writing every element one by one. And then I'm going to manipulate the same memory, but in an even much more direct way. So instead of using the functionality of the array that is there, I am actually going to write directly into memory addresses, and I'm going to do so by using the card command. And the card command is basically to directly read or write word values into memory. And the card command, it has to have an address that's an even number because it writes 16 bits. And I'm going to tell it to write at this buffer screen plus the value of I, which I'm going to increase in steps of 2 from 0 to 31,998, and writes the random 16-bit values. And as you can see, it's asking me for a key to start, and I press the key. It now executed drawing the 20p boxes, but because the shifter is not looking at that location, nothing is happening on screen. But if I start writing into the array, you can see these random bytes. They result in a random black and white pixel pattern getting on the screen. So this really shows that writing bytes can actually really result in graphics drawing. Because the shifter doesn't care what the contents of the bytes is. It's just reading this 32,000 bytes all the time and displaying them on screen. And what the bytes are, what the values are, and how the bytes and the values got there, it really doesn't care about it. And of course we can see the array fill command, yeah, it creates the nice pixel patterns that I was expecting, and it's also a lot faster than writing them one by one, which is kind of cool. And I'm using the array fill command now to turn the screen completely black. And now I'm going to bypass the array, so write directly in memory into the space that actually was supposed to be for the array. And as you can see, that also works. So with the card command, and the speed is about the same as writing the values in the array. Which is to be expected, because actually this is something that we already did in the previous part. We created an array, so the memory that was there was supposed to be allocated to use with the array, but actually my graphics commands were just writing the bytes, bypassing the array functionality and then putting the bytes there. Instead it was happening off screen. Now the same sort of thing is happening on screen. So we really need to let go of this connection between the different kinds of writing bytes and graphic commands and what the shifter does. They all do their own thing, and you can just basically manipulate any way you want. And of course now I'm going back to my default screen, where apart from the press any key to continue text, the 20 random p boxes I drew are actually still there, because those commands wrote into the memory, and now I've told my shifter to read from that part, so it's displaying them. They were always there. And of course that gives us the opportunity to, we know now that we can use memory manipulation commands to actually manipulate the graphics on screen. And to prepare ourselves for that, we also need to structure our preparations for programming a little bit. So from now on, I'm going to write every program based on a standard template. And the template is not something I completely came up with myself. It's just the stuff that was available on the forums in the past and stuff that I got from the GFA manual, and I manipulated it a little bit. But basically for every program now, I'm going to do some general preparations to prepare my memory for all the stuff that I want to do. And then I'm going to do some program specifics preparation, which can be like some arrays or some variables I want to set, etc. And in this case, I'm always going to my buffer screen, do some pre-draw procedure, because I'm sort of drawing the graphics that I want to work with. So I just left these there. And then there's some space to do some procedures for my main program, whatever they may be. And then I'm going to end it with an end sequence, so to notify me like this is really the end of your program. And then do some general cleanup to undo some of the stuff I'm doing during the general preparations. Because if you don't, you are going to get into trouble. And the persons who posted this on the forums some years ago might even be looking at this video right now and seeing that I'm happily reusing what they did for my program with their permission. Because you don't have to make up everything yourself. There's lots of information available, which just basically get some general stuff you can put in your compiler, or you can put in manually if you leave them commented out. The most important two ones, I'm not going through the whole thing, but basically disable the mouse, go to supervisor mode. So if I execute some command that I need this for, I can actually do it. It's going to check if it's compiled. If not, it's going to use the reserve command. And the reserve command is something I want to explain because there seems to be some confusing about that one. And especially the relationship between the reserve command and the malloc command I'm using here. Because I'm still creating a pre-draw buffer, but instead of dimensioning an array, I'm actually directly allocating the memory using malloc, which stands for memory allocation. And in this case, I prefer to do my pre-draw screen, so my buffer screen, always in a separate allocation of this. This one is always there. And then read the addresses just the same way as I did before. And if I need more graphics or some buffer I want to allocate in memory, I can use these lines. And basically, in this case, it's 32K. For some code, I actually use like 640 kilobytes if I want to store lots of screens of data. And I prefer to have them separate, so those operations are always separate from my buffer screen. It's just a personal preference. You can do it the other way around. But of course, and I'm going to save some stuff and make sure if there's an error, I go to the general cleanup, so I don't keep not in the middle of some configuration that I need to undo. And a general cleanup is basically I free the memory that I allocated, make sure I'm actually in the default screen, so the physical screen variable, which I never change with my code, clean it, the screen even, and make sure that my logical screen is exactly the same number as the physical screen. So you can use the same variable for both. It doesn't really matter. As long as the numbers are the same and at the correct location, you are back to the default location for your graphics commands in your shifter. Then it's going to restore a bunch of stuff I saved and make sure any music was playing, and they go back to user mode, and then also cancel the reservation that I did in the beginning. And that one is also really important, because if you don't do it, the reserve that you did in the beginning will remain like it was. And to show it, I actually prepared some code, and I also prepared some slides to visualize it, because we are doing a different way of allocating memory for our screens. And I want to discuss the differences between them. Because what we did before is, by default, GFA Basic basically uses all the free memory it can get. So there's like a little more than 200 kilobytes, 210 or 20 reserved because the operating system is there and the GFA Basic interpreter is there. And on the top of memory, there's 32 kilobytes reserved for my default screens, for my graphics commands and for my shifter. And all the memory in between, with some free space before the logical screen, that is the amount of memory that my programs will use. And I was dimensioning an array to get my pre-draw buffer, and then this is how I was doing it. But if I want to allocate memory, the malloc command tries to allocate the memory outside of the memory that GFA Basic is using. So it's really like looking for free memory that's not in use by anything. And to be able to do that, I have to tell GFA Basic first to not use up all the memory, but only use like a certain amount. So the rest of the memory is free for me to allocate for whatever I want to do. And that's what this visualization is representing. So in this case, I told GFA Basic, don't get the whole 3/4 of a meg that was still available. But in this case, do like 320 kilobytes. Any area dimension or like variables or code I do is still all happening within that reservation, but my allocation is happening outside of it. So the key is the reserve command is not to reserve as much memory as I can, it's actually to reserve less memory. So I tell GFA Basic to reserve less memory for itself, so I'm able to allocate more for my own personal usage. So that's important to know. Reserve less to be able to allocate more. And that's how it is. And to show that's indeed this is indeed what is happening, I've created some show and tell code where I'm going to basically use the FRE command I put a 0 here, so it will do a garbage cleanup, and then it will tell me, okay, I did the cleanup, and this is the amount of memory that you have for yourself. And I'm going to keep doing that after certain actions I do. And then I'm going to use the reserve command to actually restrict the memory for GFA Basic from the default to, in this case, like 128,000 bytes. And I'm going to read the memory again to see if it's indeed working. Then I'm going to do a memory allocation, in this case into a variable. I'm going to read the variable malloc, and it's an allocation of 0.5 megabyte. So if this allocation would take place within the reserved memory, it would not work. And if the allocation is not successful, the variable will have a value of 0. If not, it will have the start address of this allocation. So I'm going to also print those on screen. What I'm then going to do is I'm going to move some data, and I'm going to use the bmove command, which we will discuss in the next video. For now, it's important to know what I'm going to do is I'm going to move from my screen address, from my current screen, I'm going to move 32,000 bytes to the address that's held by this variable. And then, of course, I'm going to see, like, does it have any influence on the free memory of my program, which probably won't, because it's all happening outside my memory. Then I'm going to dimension an array and get the start address of the first element of that array, and then see, okay, if after I created this array, how much memory do I still have left, and where is the array actually situated, so where's the start value. Then I'm going to bmove again, but instead this case from my screen into the array with the same amount of bytes to see if that has any influence. And in the end, I'm going to free up the memory again by erasing the array, actually freeing the memory that was allocated before, and then doing the reserve command without any arguments, which basically means go back, so cancel the reserve that you did, and it will go back to the default configuration. Then I'm going to check my memory again after cleanup and to see how much I have left. So, sorry, that was a lot of explanation, but it's just to show the effect of the different things. So by default, my memory for my program, as you can see, is like 3/4 of a meg, which is like the situation we have here, even without the array. So the total reserve is about 3/4 of a megabyte. And after I do the reserve command, you can see that's now been restricted. And that means I can allocate 0.5 megabyte. And you can see that the allocation was successful, which means the allocation is happening outside of the memory assigned by the reserve command. So I restricted GFA Basic to be able to allocate this huge amount of data, or this 0.5 megabyte. And yeah, you can also see the start of the allocated memory is actually outside of my reserved memory. So this 200 something plus 128 is like 375 kilobytes or so. And you can see that after that, my allocated memory starts. Of course, if I do a move of data into this allocated memory, nothing changes, because A, the allocation was outside of my reserved memory anyway, so it will not be displayed. And B, I allocated the memory, which means the bytes are in use. And if it's all zeros or all ones or anything in between, the values of the bytes don't matter. The bytes are already allocated, so they are using up the memory. So that the number won't change, this number. Of course, after I create an array, which is happening within my reserve, because it's like a bunch of variables that my code is creating, so everything it does is inside this reservation, which means now I have 32 kilobytes less of data left. And also in this, the array is created, the memory is already in use and reserved for the array. Nothing else can, it will not allow to do anything else with it. And you can see that the array is actually within the reservation, so right after the memory for TOS and GFA Basic Interpreter at the 215 kilobytes-ish mark. And of course, if I do a data move to the array, in this case also, the bmove just changes the values of the allocated memory, but it doesn't change the amount. So the amount of memory is still the same. It was already allocated and is now still only already allocated. So it doesn't change anything. And of course, after I release everything and clean up, I have the 0.25 megabyte to myself again. So what we really saw happening is that in the beginning I had this situation, And after I did the reserve command, yeah, the green part got smaller. I reserved less to be able to allocate more. In this case, it's 0.5 megabyte. And we could see that actually the dimensioning of the array made the situation that there was less available memory inside my program. But putting data there didn't change anything. So that's just to show you the differences between them. And there are some really important things to remember, because now everything went okay and everything was given back after at the end of the program. But suppose I wanted to allocate memory and I said, well, I want to allocate 812,000 bytes instead of 512,000. And we already know that the total amount of memory I had from my interpreter anyway was like 3/4 of a meg. So this is not going to work. And that also means this variable will have a value of 0. And that means if I do this move command, I'm trying to move data to a memory address of 0. And I'm not allowed to do that, because memory address 0 is where the operating system and stuff is. And since I'm in user mode now, I'm not allowed to write there, which means at this point my program will bomb out. It will force a bus error, say 2 bombs, and if it were a program you would see 2 bombs in screen and you would exit. Now it goes back to the interpreter. But it also has some other side effects, and that's what I want to show you. Now this is successful, my reserve command is successful, but as you can see my allocation was not successful. It could not allocate the 812,000 bytes because there's simply not enough memory available, which means the variable is 0, and now I'm trying to do move data there, and they say no, that's not allowed. 2 bumps, bus error. You are doing something in memory that's not allowed. Something is going wrong. So now it ended the memory, but it also means it didn't execute any of this, including this freeing of the memory. So if I try to run the program again, and I'm just going to do the malloc like a very small amount, in this case just 12 kilobytes. But if I start it, the reserved memory is still only 128,000 bytes. So it didn't cancel the reservation command. It means also if I do this in a program, and even if I load a different program, this will still be this configuration will still be the same. So whatever you do in your preparations, you really have to undo in your post cleanup. That's why I start and stop with the same procedures every time. And of course the reserve, is in this case it's the same. The allocation, because it's a tiny amount of data, is actually successful, which means I can do the rest of the program without problems. And also it means now it's doing the cleanup at the end. And so now I have the 750 bytes. And that's why those on error goes up general cleanup and on break goes up general cleanup was there in my preparations. So whenever I break a program, I make sure it does the cleanup so I'm not into trouble, because you can get some weird effects. And even if I'm just doing this tiny amount, there's some you can see that manipulating memory can be quite tricky. And we saw already like doing an allocation that doesn't work. Yeah, if it's not successful, just end your program. There was a check there that said if the allocation is not successful, just go to general cleanup and just exit the program, because there's no using going on. But also, if I do this allocation, and it is actually successful, but for some reason I was typing here, and instead of malloc I type MALLOC. So I make a typo. Up to this point, I did everything correct, but because I made a stupid typo here. In this case, because GFA Basic is a very flexible language, so it means if I type just a variable in the middle of the code, if this were like modular 2 for instance, the program would refuse to do anything with it, because it's a variable that I didn't declare and define at the beginning of my code. So it will say undeclared variable, I'm not going to do anything. But GFA Basic will read it, say, this is a variable that I don't know. It will assume I want to use this variable, create the variable for me, and then give it a value of 0. Which means if I'm working with direct memory manipulation, in user mode it will just disallow me. If I was in supervisor mode, it will actually allow to execute the command. So in this case also, because I'm in user mode, it will do the same bomb out message, and you can see that everything is successful, but now still I get this bus error because I'm still trying to write to a value of 0 because of the typo I made. If I'm in supervisor mode, if I'm lucky, it will bomb out with 2 bombs. If I'm in bad luck, and I've actually experienced this already when sort of experimenting, if you're in bad luck, it will just execute and the whole system will hang, because it's writing in the memory where the operating system is situated, and it will just, instead of bombing out, the system will just completely halt, and you have to like manually, you do have to do a hard reset. So this is very important to realize. If you are working directly in memory, you should really be very careful. And yeah, now you see that the reserve wasn't undone. But now I can go to the program, and you see that now it's an error while reserved. So something else happened. Because I had an error in the middle of the program, GFA Basic sort of gets confused, and it's really hard to get back to the normal situation. So be sure anything you do, you clean up, and make sure you don't make any typos, which means also before you test your code, make sure you save it, because if it goes wrong and you try to save it afterwards, you might even lose some of your code, some of your data. That's basically the most important thing I wanted to tell. This was mainly about theory, this video. But we need this foundation and this realization before we move on to manipulating memory to move graphics. But that is exactly what we are going to do in the coming videos, where we'll take a look at some simple scrolling, but we will also optimize our sprite routine a little bit more. And in the next video, we will going to look at this bmove command with a little bit deeper, with a little bit more detail. So looking forward to that. I would like to thank you for watching, and I hope to see you next time.